Hi everyone, my name is Yaoyu Zhao. I'm a PhD student from the lab at EPFL. Today I'm giving a talk about to discuss our journey migrating a large-scale Scala'25 project to Explicit-nulls, these new Scala'25 features. And during this talk, I will describe the task and explain the problem we encountered, and I will describe some details about the migration approaches we take, and explain how do we integrate LLM into our tools. We'll talk about some details, how do we design the prompts and our workflows. We talk about more about how do we do the review and validation about our migrations. Then we will talk about our migration results. Now, let's think about the situation. You are given a task. You need to migrate a large code base to the new Scala'25 features. And this is really a large project because it contains about 200,000 lines of Scala code. And if you just simply enable these features, you will get about more than 600 about the errors immediately. How are you going to start your migrations? The truth is, this is the task I was given a few months ago. And the project we want to migrate is the Scala'3 standard libraries. Before 3.8, we used the standard library from Scala 2, but unfortunately, we couldn't use any new features from Scala 3. So the standard library itself is unfrozen in 3.8, so this is a good opportunity for us to enable these new features. And you can check the new standard library in this link. And the new features we want to implement, we want to use is the Explicit-nulls. So before we talk into the details about the task, I will first give some quick overview about the Explicit-nulls. Explicit-nulls is a new feature for Scala 3. It modifies the Scala type systems, which makes the reference types or anything, a subtype of any ref, non-nullable, such that the null or the lower capital null is the value of null, and the null with the capital letter N is the type of null, and such that null type is not a subtype of string anymore. So when you're trying to assign the null value to a string, you will get errors with the Explicit-nulls. To represent something to be nullable, you need to use the union type, such that, for example, here the variable b has the type string or null, such that in this case, of course, calling the method of string on a nullable value is unsafe anymore, so it will give you errors when you're trying to call the trim from b, saying trim is not a member of string or null. In able to cast it, you can still cast it a nullable values into a non-nullable values using the .nn, but it will still show null pointer exceptions if the variable is truly null during the runtimes. You can find more details in the documents of Explicit-nulls. Of course, these features will modify the type systems, will modify the type hierarchies. When you enable these features, your code will break. And we do care about the compatibility. So we already implemented several improvements in the compiler to help users to gradually migrating to these new features. We have the flow typing to check the nullability in the control flow. We introduce the flexible types, such that the types from the unsafe world, from, for example, Java, you can treat them as nullable and non-nullable at the same times. We also introduce the unsafe nulls, so this is a language import. So you can temporarily disable the Explicit-nulls in some scope of your code if this part of your code is extensively working with null values. You don't want to check the nullability through its type. Then the motivation is that why do we want to migrate standard libraries to Explicit-nulls? Well, the kind of limitation is that we would trust the type from the Scala code which is compiled without the Explicit-nulls. If this is based on the assumption that most Scala developers don't use nulls that often, so it's probably safe to trust them. But if you have the type from Scala, which is say string, we will treat them as string in Explicit-nulls. Then this would introduce the problems, such that in the standard library, so we have the apply function for options. It takes a parameter of A. We will check if the parameter is null. In this case, we return none. If it's not, we will return a sum. But if we want to use this in the Explicit-nulls, if you want to transform allowable values into an options, for example, in this case, you want to transform allowable string into an option string, then it will fail. Because when you apply the option, the type parameter will be inferred as string. So you couldn't pass string or null to option in this case, which is pretty bad. So with explicit-nulls, of course, we do have a right choice to give the true null safety for these signatures. You really want to change the signature of the apply such that it actually accepts a or null. Then in this case, you can actually pass in string or null to the option, and it will actually return the option string. Well, we talked about why do we want to do the migration, but what's the first thing you will encounter? You will have more than 500 of errors initially. So the errors look something like that. So it's basically if you are assigning null to some values which is not nullable, or you're passing a nullable values to something which shouldn't be nullable. And of course, this is just the initial errors. But during the migration process, if you're updating the types, you will get more errors. And also because of dependency, you can also get some different errors, such as you are selecting some members from nullable values, or you are violating some bound, etc. And during migration, you will also see some crazy code from a standard library. So I copied this line of code from standard library, which is the collision-proof hash map. I copied it exactly, so it will return a sum of null values, and it will also return null. So it is actually return the result type for this is sum or null. And this is, we know this, they are doing this for reasons because you are using null to represent some unsuccessful operations. But this violating the lessons we teach the beginner of Scala, like you shouldn't pass null to a sum, and you shouldn't return null for option type. So to estimate how many trainings we need to do the migrations, we can first just search the literal string null in the library of all the Scala code. There will be about 1,600 of places using null. So at least all of these places need to be updated. How do I say the difficulty of this project? Well, I wouldn't say it's a difficult task because if you are experienced Scala developers, looking at the code, looking at the error message, looking at the comment, you know what's the correct way to fix them. But it is a tedious task because as a human, you need to read all the code of the standard library and you need to understand all the error messages at the same time, hundreds of error messages, and you are doing all the migration at the same time. It's a nightmare. If this was 2 years ago, I have no choice. I just manually do the fix. And this is what happened 2 years ago when we enable explicit-nulls for the Scala library itself. And I can tell you it's a difficult task. But now, after 2 years, with the development of the new tools, is there better tools we can use? Why do I say this is a difficult task at the same time? Now, we can consider concrete examples. Suppose in your code, originally you have a function which takes a type A and you are returning a type B. Then by looking at the body of this function, if you are calling the method on the parameter directly, then the code is probably assuming this parameter to be non-nullable. So you should keep the original type. At the same time, if you code at the beginning, you are checking this thing to be non-nullable, using some assertion or throw exceptions, then it should probably also not change the type of parameters, even though it can be nullable at the beginning, but we should keep the original types to encourage people to passing a non-nullable values to these functions. By looking at the body of function, if your logic is depending on the nullability of the parameters and you are doing things differently depending on the nullabilities, and you are also returning null in some of the branches or in some cases, then, for example, in this case, you should updating the type for the parameter and the result type to the nullable types. Well, this sounds like a good guide to do all the migration, but we do always have some exception in the standard libraries. There will be some places you don't want to add or null. So for example, here, this is a conversion function we take from the standard library. It is an implicit conversion which from IRA to RSX, such that you can use all the array operations on the IRA. By looking at the body simply, it tracks the arguments to be null or not, then it will return null if the argument is null. Well, according to the rules I said in the previous slides, I should probably change the argument type to nullable and the result type to be nullable. Is this a good choice? Well, what would happen if we passing a non-nullable value to this function? It will still return a nullable value. So if you want to do further operations on the result, you need to add .nn, even though you know it is not nullable. So of course, we need to do something to check that if you are passing a nullable values, you get a nullable values. Yeah, if you are passing a non-nullable values, you should get a non-nullable values. We can achieve that if we are able to use some match types or some inlining techniques. But we are also migrating the standard libraries. We have lots of constraints. We cannot just simply add a new definition to the standard library. So the final decision is that we keep the types as non-nullable to encourage people to not passing a nullable values to it. You should check the nullability before you use it. Another case we want to keep the original type is something like this. If you have a field which is initialized to some value and you working with it in some period, and after, for example, in this case, after evaluation, you assign it to null for garbage collections. Well, of course, you can say the underlying field should have the nullable options because you are assigning a null value to the field. But if we do that, you need to add a lot of .nn or to the code, and you're also flow typing sometimes may not work. So even though your code assuming a lot of places to be non-nullable, you are still you don't know, you are not able to check nullabilities in a lot of places. So in this case, probably it's better to keep these types non-nullable. All of the slides I'm saying is saying that this kind of migration we want to achieve is not simply to fixing all the errors. We want more deep semantic understandings. Because we are working with the standard libraries, we are also facing some constraints. We want to preserve the runtime behaviors. We want to make sure the binary compatibilities. We want to make sure the API we updated is matched with the semantic requirements we want, such that the simple tools like if you want to use Scala fix to just simply add .n to every places you have nullable values is not good enough. We want a tool which can understand our code, which can understand the comments, can understand the error messages, and it can achieve the behavior we intended. So what tools do we have? Oh, okay. After 2 years, we have the large language models. It seems to be pretty good at this kind of techniques because the large language model can understand code. It can read your comments. It can do all the sorts of generations. It is trained to do specific programming tasks, and it's because when you communicate with the language model, you are communicating in human language. You can describe your requirements in human languages, and it can explain the changes in human languages. I wouldn't say the large language model is smart enough to replace all the people, all the programmers, but I think it's good enough to do this kind of jobs. So our initial migration approach is just like a simple Q&A style of large language model approaches. We collecting all the error messages, and we just ask large language to fix them directly. Like if I saw like these files contains errors, I just pasting all the errors into the large language model, and I passing all the whole files to it and ask it to fix. Well, it's actually pretty good at the small files. And because it can understanding the error places and it can modify multiple places cohesively. But it fails at a large scale. If I have a file contains thousands of lines of code, if I pass all this to a large language model directly, it will doing something weird randomly. It can deleting the code randomly. It can modify the comments randomly. So eventually, we have an enhanced approach with the large language model, such as after we collecting all the error messages, we will first group the error messages together in, like, if this function contains 5 error messages, then it must be related together with the parameters. Then we will collecting the code around the error messages with some context at the beginning and at the end. Then we also design a more detailed template for the prompt to give the large language model a specific rules about how to fixing the code. And we get a lot of benefits. Rather than passing the whole files to the model, we can reduce the token usages. It has a better local correctness. And I can simply just passing hundreds of files processing at the same times. And here is like the prompt I designed for this kind of task. At the first, I will give a specific task, and I'm asking the model to fix the errors only related to explicit-nulls, and it should follow the following rules strictly. And then I will pass in the error messages relating to each other, and then I will put the code together. Okay. Okay, it did a great job, and I think for this project, most of the changes is done using these approaches. But it also has some limitations. It sometimes can also, it may not find the best approach at the beginning, so we need multiple try at the end to find the best migration choice. I may sometimes need to step in to make the changes I want and to guide the large language model to do the migration in the remaining errors. So this is kind of changes it made at the end. So it is able to change the field to null and add the annotation we want to enforce flow typing. It is able to update the signatures. It's able to add .nn at the places you are only able to check nullabilities through some other logic. It's able to update the result types as we want. It's pretty good. So at the end, the total change is about like 1,500 lines of code. Well, you are saying most of the changes is done by AI. How you are going to trust that? Should I trust human more? Well, of course, we have a lot of testing by the compilation tests and the community project tests. We are also using a hybrid approach to ask for review from both human and the large language model, because I will give a detailed document about how you should do the migrations. You should do this in this case, you should do this in this case, and we are collecting the review from both sides and do the final patches. And surprising is that even though we trust human more, there was a typo in the changes. We couldn't, after few rounds of human review, we couldn't catch that. And it's not catched by the testing as well. It only be caught by our, like the coding agent at some point. So I was just saying that the large language model can make mistakes and the human can also make mistakes. So this is my workflow in overall. We first collecting all the error messages. We run the script to invoke the model to apply the changes. And optionally, we will step in and make changes we want. And we recompile again until everything is compilable. Then we run all the tests and community projects. We do all the hybrid reviews from both human and the large language models. There was something I want to do, but because of time constraint, I wasn't not able to do before I finished this project, is that because the way we are doing is that it is mostly working with the same files, so it's not able to looking at the whole code base at the same times. We are also looking at the edits before the current files. It is also not able to do the SBT or methods, but I think it's probably doable. And I also wrote some prototypes, which is really simple if you are using some AI frameworks such as non-graph in Python. So as a result, we successfully migrate the standard library, I would say, such that we don't have any behavior changes. We make sure the binary is compatible with the previous standard library, such that if you are not using Explicit-nulls, using the new library shouldn't change anything. And we also sure everything pass our tests, all the commit builds looks good, and it will be ready for the next Scala version, which is 3.8. For the existing projects using Explicit-nulls, the only noticeable change is in pattern match with regular expressions, because we do update the types such that it will actually tell you the result should be a nullable string. And I'm proud to say that all the core components of the Scala3 has been fully null checked, which including the compiler, the standard library, the Scala doc, and the presenting compilers, etc. You can actually try the new standard libraries with Explicit-nulls if you're using the Scala CLI, such as if you specify you are using the Lightning version of 3 and you enable this Explicit-null flex. And thanks everyone. Hopefully we can push the Explicit-nulls to the next level in the following year.
Thank you. That was a lot of work, I imagine. Do we have any questions?
Hello, thanks for the talk. So in the final PR, maybe you said this, but maybe I missed it. So was it just changing the signatures and ending .nn, or was there some bug fixes that surfaced as well?
Sorry, can you repeat?
So in the PR, migrating the standard library to explicit nulls, was it all changing signatures, or did you fix some code in the process as well?
I think it is focused on changing the updating the signatures. We don't change the code behaviors because.
But maybe you found some bugs in the process of updating and by running the compilers, maybe the compiler found some bugs really.
We didn't find any serious bugs. It's just like of course we need to updating the compiler as well because it has a better types when you comparing together with the standard libraries. We do need to insert .n in some cases, such that, we have the flow typing. For example, if you compare a variable with null, then at the branch you can assume it to be non-nullable. However, if the nullability depends on some other logic, like if it depends on some numeric variables, then flow typing won't work. So we have to insert .n in this case because we assume it to be non-nullable at this point.
Okay, one more question.
Hi, thanks for the talk. So I was wondering if you have kind of like some estimation of timeline on like how much we spent on actually running the LLM or developing an approach to the thing and then doing comprehensive review. And do you think like in the end we save time?
Yeah, I do think it saves a lot of time for me. Like especially for the first step to do the migration. If I would do it manually, I have to look at all the error message, and if I change one places, there are a larger error pop out at other places. It's just tedious. And if I use my tools, I can just do all the migration at the same times, and it will give a pretty good result at the beginning. Of course, I need some manual to review. Reviewing all the changes is much simpler than to actually writing all the changes.
Something a little bit detailed, like you did say that there are some places where changing the code to fix one thing will pop up errors in other places, right?
Yeah.
Is that something you kind of have to do in a loop with an LLM?
Yes.
Or
yes. For example, if we figure out that the result type of a function should be nullable, then everything depends on this function needs to be updated eventually. It's something like that. So yeah, it is updating a loop. So it will first updating function, and in the next iteration, it will find new errors. Then we apply the tool again until everything is being fixed.
Okay. Okay, thank you, and let's thank him again.